Welcome. To find maxima or minima of a function, we need to look at critical points. Let me give you the definition. So x is a critical point of f if f prime x is equal to 0. So this means especially that the function is defined and also the derivative is defined here, and so that this makes sense. This is a simple definition. That's the definition which we usually take in mathematics as a critical point. So we don't look at points where the function is not differentiable. So in the case of the function, let's take x squared plus 2x plus 3, then when we just look where the derivative is 0. So f prime x is equal to 2x plus 2. That is equal to 0 for x equal to minus 1. So in this case we can draw the function. This is a parabola, and actually finding this place where the derivative is 0 helps us to draw this function. So we see that at x equal to minus 1 that happens, and at x equal to minus 1 we get 1 minus 2 is minus 1 plus 3 is equal to 2. So the function goes here through that point. And it's a parabola which goes like this. Pierre Fermat realized that if a function has a maximum at some point, just make a picture here, then the derivative has to be 0. It has to be a critical point. We just formulate this. If f has a maximum at x, then f prime x is equal to 0. It's a critical point. It's obvious, but very, very important. And let's just quickly prove this. So if f prime x is not 0, let's assume it's positive. If it's negative, we would just go backwards. So if f prime x is positive, then fx plus h minus fx over h is, so let's call this c. Then this is bigger or equal than c half for h small. So what happens is, let me just make a picture here. Assume that the derivative at some point is positive. Derivative is positive. Then it means that for close enough to x, the slope of this secant line is bigger or equal than c half. Something close to c. So that's the... And so fx plus, we can say fx plus h is bigger than f of x plus ch half. So that gain which we do here, we gain about c, but definitely more than c half. And so this contradicts that we have a maximum. Right, because we went up by this amount. So it's very clear, right? If you are on a slope, in the snow, on a slopey hill, and the slope is not 0, then you climb up, you can climb up. And if it would be negative here, then you would just go backwards to climb up. Critical points don't necessarily correspond to maxima or minima. Right, the very important example is x to the 3, which you always should keep in mind. X to the 3 has a critical point here. So x is equal to 0 is a critical point. But it's neither a maximum or minimum. So we cannot reverse that Fermat theorem. But there is a reverse, and that's the second derivative test. We just write this as a theorem. If x is a critical point, and if the second derivative of x is positive, we just write x naught, so to make it clear that this is really a point, then x naught is a local minimum. Of f. And the second statement is if f2 prime x naught is smaller than 0, then x naught is a local maximum of f. Now there's a third part. If f second derivative is equal to 0, then we need more more information. So the theorem doesn't really tell us whether it's a maximum or minimum. So in the case which we have just seen, f is equal to x squared plus 2x plus 3 before, so we have f prime is 2x plus 2, f2 prime is equal to 2 is positive, so that's positive means that x is equal to minus 1 is a local minimum. Actually, it's also a global minimum overall, and so that was this parabola had there was a minimum here at minus 1. That's the second derivative test, and it's kind of clear what happens here. This means it's concave up, right? If it f2 prime is concave up, is this situation. If it's concave up, then we have a minimum, and the concave down means we have a maximum. Here, this is the situation where we actually have f2 prime is equal to 0 in this case. So we have a situation where things don't apply. Okay, it's already late at night. I have to wrap it up. Let's just make two examples. So the first example is we have a function f of x, and we want to find all critical points. We want to classify them according to maxima, minima. So f is equal to x to the 6 minus 3x squared. F prime is equal to 6x to the 5 plus 6 minus 6x, and that's equal to 0. So what helps is that we factor things out. So f prime is equal to 6x times x to the 4 minus 1. That's equal to 0 for this is 0 for x is equal to 0, 1, or minus 1. So there are three critical points. And let's just also compute the second derivative. f2 prime x is equal to 30x to the 4 minus 6. And f2 prime, we have to compute it at every point. This is minus 6. f2 prime at 1 is equal to 24. And f2 prime of minus 1 is also 24. Okay, that's equal to that. So in both cases, here we have something positive, and here we have something negative. And so we can say, we can make a list of all the points. So we have 0, 1, negative 1, and then we have the types are, this is a minimum, and it's negative, so now it's a maximum. This is positive, so this is minimum, and this is also minimum. So these are the 3 points, and we can also draw this function. In this case, this function actually goes through 0, and we know at 0 it is a maximum. So because it's a maximum, we know it has to go like that. And then we have another critical point at 1 and -1. Let's just take this -1 and 1. So we know at 1 and -1 it has to be a minimum, so it has to turn around here. And then we also see that this function actually, you know, grows much faster than that, so we have again we will have a point where this is actually going over. So I think this is square root of, so the fourth root of 3 here, where it goes through 0, but then it goes to infinity. But these were the critical points. There are 3 critical points: 0, -1, and 1. And at these points, the function has horizontal tangents. So it's here in this case we have seen it's concave down. So this is concave up. This is one of the standard examples which you see first is a maximization problem. We want to see which rectangle of circumference 6 has maximal area here. So if it has circumference x, if this is x, then this is 3 minus 6. This is also x, this is 3 minus 6. If you add them all up, you get 6. So the circumference is fixed. And we want to maximize the area. So the area, of course, is a function of x, which is x times 3 minus 6. And so we can take the derivative. So this is 3. We can either use the product rule or multiply it out. Maybe simpler is to multiply it out. So this is 3 minus 2x. This is equal to 0 if x is equal to 3/2. So you see that if x is equal to 3/2, this is also equal to 3/2. And so we see that the square maximizes the area. So this function, if you actually, this function is 0 at 0 and it's 0 at 3. And so this is a parabola here. And so this is f of x. And at x equal to 3/2, we get the maximal value. And in class we will look at more examples of such extremization problems. So see you tomorrow.